Hello everyone, and welcome to Engineers Ireland. Today what I would like us to cover, or at least to begin on, are series and sequences. Now this is a chapter that most people seem to avoid, and if you look at the questions that are answered in the Leaving Cert, you will actually find that the ones on series and sequences have much less people doing them than the other questions. Now they're very important. They're important because stuff you learn in this makes the special question in part B of paper 2 much easier. Along with that, this section isn't as hard as you may think. All that you can say is that it's a little unfamiliar at the moment because you're playing with names of mathematics that you wouldn't have normally come across before. We did cover recurrence relationships, and in that we actually came up with a new way of naming terms, and we would talk about UN, and like the U3 is obviously the third one in this particular sequence of numbers. Okay. One of the reasons why we covered that section before this is it actually introduced you to that naming system, and we'll be continuing with it and variations of that naming system now. There's basically two main parts to the chapter. The first one is leading us into telescoping series. You will find that that comes up in the special question. The second part I always found is much easier than the first part, which has to do with finding the sum of an arithmetic series or a geometric series. And there's some nice interesting stories or little interesting series that you can actually look at and you can prove different ways. So anyway, let's start. What we're basically saying, as before, that's our naming system. We're saying the first one will be U1, the second one is U2. Now it can belong to almost any sort of a thing. For example, this very simple one. The first one is 3, the second one is 5. Now there may well be a relationship between these. Now it doesn't take a genius to figure out that each one is just 2 bigger than the previous one. So we'll say 3, 5, 7, 9, 11, blah blah blah, and on. But in many cases the relationship between one of these and the next one to it isn't as obvious. But let's look at this. We're saying the general term here is UN. Now we could have been given a situation, and this is straight from the book, where UN is n squared minus n plus 3. What you will notice is, when we go back up to the top line again, U1, it's the 1 bit. We're saying the first number. U2 is the second number. This is the third number. So that's where the n bit comes in. Notice it over here. The nth one. If n happened to be 17, we'd be saying it's 17 across in the set. So now down here, when we're saying UN, we're saying at the nth location, the answer is going to be the number n squared minus n plus 3. So it would be pretty obvious then that U1 is equal to 1 squared minus 1 plus 3, which is 3. Now a nice little interesting thing you'll notice about this, look at the first series. We have a 3, a 5, and there's a 7. Here, 3, 5, the last one is a 9. You need to be really careful when you're dealing with series and sequences. It's very easy to jump to a conclusion with these things. The least you really need are 3 of them, because when you have 3 of them you can play around and you can get a general sense of pattern, okay? And especially for the kind of series that you have for the Leaving Cert, 3 will generally do it for you. Now then, having looked at how these things build up, any form of equation that we'll be given and we're told is a UN means we can actually work out numbers for it. So for example, and it's one of the examples in the book, UN is n squared minus 2n. So we'll say U4, the fourth one, will obviously be 4 squared. Pretty easy. The reason these ones are easy is they're getting you used to the concept of the naming system. And the naming system, as you can see, has the lovely quality that it is consistent, and it isn't all that hard. You just need to practice and change something that's unfamiliar to being familiar, because this is not hard. Now, one of the things you can do with these things, when we know a relationship like this one here, is we can ask certain questions. And one of the questions that's been asked here is, what value of n will give us 35? So let's look at it. And we'll say, what value of it will give us 35? Now look at how fast you move back down into junior cert mathematics again. And now you can factor. Now this is a nice little example because it shows you an important thing. It's a bit like you can't go down to a shop and buy -5 apples. It's not possible. You have to buy, you can't even buy 0 apples. Technically you could argue you can, but a shopkeeper wouldn't be too happy with you. They'd be happy to see you buy 1, 2, 3 or whatever number. But the idea that we could have a series where we're dealing with the -5th one in the series, it just doesn't work, okay? So this is not a valid solution down here. So the only valid solution here is 7. So we'll say when we're looking at the 7th one of these, we would be able to say 7 squared minus 2 7s should be able to give us 35. It doesn't take a genius to work that one out again. Now, we've already discussed this way of dealing with terms where we're using n, and it does function exactly the same way as we had talked earlier, that it's like dealing with an f of x. If we're saying when x is 5, you can shove in 5 every place you find an x. Also, if you wanted to know what happens when you've got an x plus 1, you just shove x plus 1 in everywhere where you have an x. The same thing works here, okay? If un is equal to 2n plus 1, notice every place we want to put in where we had an n over here, we're now going to put in an n plus 1. Straightforward. Again, these examples are given just so that you gain experience, so that you don't have to be wasting your time thinking about stuff and the clock will be ticking against you in the Leaving Cert. I'm deliberately going to go through the second example here because one of the other areas that people seem to have a lot of difficulty with is dealing with this type of thing. factorials. For some reason they have difficulty. So we're saying this is the one where the nth term, the un, is factorial n multiplied by n plus 2. So what is it? And I'm not going to go through all the example, I just want you to see this. Obviously un plus 1 will be equal to n plus 1 factorial outside of n plus 1 plus 2, and we'll say that's equal to now if we were asked to play around and find some sort of relationship between the un and the un plus 1, it's important that we know how to be able to convert something like that into something like that. And obviously, because I'll just write up here in the top that 5 factorial is equal to 5 by 4 by 3 by 2 by 1, which is equal to 5 outside of 4 factorial. So we do the same thing down here. Remember, if you're not certain about what to do with an equation when it looks a little complicated, always pick an easy example like this thing up here. So we can say it's n plus 1, isn't it? Multiplying into n factorial by n plus 3. And now we have a basis that we can actually find something common. And if we are looking at, for example, that a certain number multiplied by the un term plus a different number multiplied by the un plus 1 term, now you can play with it. Another concept that you just need to take on board, and it's a very easy one, it's some series are called monotonic series. It basically means that if you have two terms, and let's say the second one is bigger than the first one, well then the third one will be bigger than the second, the fourth one will be bigger than the third, and on and on and on, and it'll keep going, that they keep getting bigger, and that would be a monotonic increasing series. Obviously, if the second one is smaller than the first one, and the third one is smaller than the second one, and that goes on and on and on, that's a monotonically decreasing series. It's a concept that you need to know, because the best way of communicating with somebody is to have at least learnt the same language as them, and these are the words that are used to describe what these series are. Now we're beginning to get to the type of things that makes this area or this section interesting, okay? And after a fashion, we're playing around, and we're going to lead up to telescoping series, and they're really useful and they're powerful, and they're certainly something that if you know how to do and to play around with them, your Leaving Cert will get much easier. You certainly don't want to be working on a reduced Leaving Cert where you're leaving out certain sections just because you didn't get used to doing something. The next concept they give you, they'll say you've got a finite series. Now clearly the only other possibility is that you can have an infinite series. Finite obviously means that there's a limit to the amount of terms you're going to use, and when we deal with that, what we're going to talk about is just use a new letter, okay? Obviously start letter is S, so we'll be using an S for these. Now S1, this is summing up a series. Well, it's equal to the first term, isn't it? Well, the sum of the first two is obviously equal to the first one plus the second one. Now don't worry, I'm not going to give you too many of these, because it becomes very obvious what we're up to here. So we're saying the S, the sum of the first n terms, is going to be equal to u1 plus u2 plus all the way up as far as the unth term. Now, how can we play around with this? If we look at this situation here, we can say that the third one, well, it's the same as the second one, only with an extra one added to it. So I can say to you, S3 is equal to S2 plus U3. So we're saying to sum up the first three is the same as if you'd already summed up the first two and you add in the extra term, the third term. Pretty obvious, of course, but this is useful because once you get your terminologies and you see how your S's relates to your terms, you can manipulate these things much more readily. Now, this also implies something else, because sometimes you're asked to work out what, let's say, the seventh term is, and you'll get certain things. So one of the things you'll get from this, if we just rearrange it, we can say that U3, for example, is equal to S3 minus S2. Okay? And more generally, the nth term will be equal to the sum of the first n numbers minus the sum of the first n minus 1 numbers. Hopefully that's clear, because again we're just building up our numbering system, our means of being able to manipulate lots of big numbers. Okay? Just to pick a simple example that's given in the book in relation to this. You'll notice a lot of these look very similar. Okay? You're saying find S2 and S3. So we're saying that's our second sum, and our sum of the first three elements are there. And we're saying, well, the second one has given us an answer of 6. The third one has given us an answer of 15. So we can actually easily work out that the third term in this series is the S3 minus the S2, which is 15 minus 6. Okay? So this is just how you manipulate them. There are three really useful little rules or tools that you're now going to be given from the books, I mean. And what they're basically saying is, remember how we talked, or we discussed them into like S, N, okay, of something. It's the sum. We could have said that S is also the first letter of sigma, this guy. Okay? And how you write this is you can say it's a general term R, which can go from 1 all the way up to n, okay, of, we'll say, un. So the third way of writing that would be u1 plus u2. And you can go across and you can say, I have my general rth one, and I go all the way up to my last one. So these are n's. That's an R. So R now is a general term in a sequence that runs all the way across to the biggest one, n. That's why the biggest one, n, is written up here. And we're saying R is allowed to vary from 1 up as far as n. So in this case R will go 1, 2, blah blah blah, general R1, and as far as n and can't go beyond n. So they're just the two ways of writing it. Now, what are the three that are of use to us? Of some constant. If we want to sum up a particular constant, okay, we'll say, oh, it's the constant, and we will have all the way across to the constant. We have a whole load of them. We have n of these, so you have n by c. So when we sum up n terms, all of which are exactly the same, the answer is obviously n times that constant. Here's the second one. Now, what are we asking? We're saying when r is 1, okay, when r is 2, when r is 3, and you say when r is r, for example, just to show it in the middle here, all the way up as far as n. So now we're talking about adding up numbers 1, 2, 3, all the way blah 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 up as far as some number you want n, and it could be 1,729,000 sort of thing, a huge number. It doesn't have to be little things like up to the first 17. And we're saying, what's the sum of that? Now for the moment you just take this on blind faith, but very quickly in the chapter it actually proves this for you. The third one. We're going to sum up the first n of terms where each one of them is an r squared. So we'll say 1 squared, okay, 2 squared, and we're told that it's equal to this. Oops. An interesting little thing just to notice. We're dividing by a 6 here, which is 3 by 2 by 1. We're dividing by 2 here, which is 2 by 1, and in reality we're dividing by a 1 here, which is 1. So this thing down here is 1 factorial, that thing is 2 factorial, and this guy is 3 factorial. But that's just a little aside. In reality what you really need to know is if you're given just the same number, it could be 5, 5, 5, 5, 5, 5, and you're told there's 25 of those, the answer is obviously going to be 25 by 5. So the answer is n by c. If we've got the series of natural numbers, 1, 2, 3, etc., all the way up, and you're saying the first 17 of them, the answer will be 17 multiplied by 17 plus 1, which is 18, divided by 2. Okay? So it'll be 17 by 9. If we've been given a series which is the natural number squared, so it'll be 1, 4, 9, 16, and all the way up, no matter how high up we go, the answer will be, if we say we went for the first 25 of these, it'll be 25 multiplied by 26 multiplied by 2 25s plus 1, and all that gets divided by 6. Okay? Now we get to one of the really powerful little things in the chapter, and that is the telescoping series, but it's going to come through by way of what happens when we look at one of these. Okay? Sounds innocent enough, but we want to show that for all values of r elements of n, Okay? Now I want to bring your attention again, this is at least the second one of these talks that I've mentioned to you guys. Watch, it's n. It's not n0. N0 includes the 0 number. This one here doesn't. It goes 1, 2, 3. So the smallest number we can look at here in this one will be 1. So let's show this, okay? What we're going to do is we'll write a little shopping list here. When the R value is progressively getting bigger, and we'll run down along here and we say, what happens? To this side here, when R is 1, you get 1 squared minus 1 minus 1 squared, okay? Now, and we're saying that should be equal to 2 by 1 minus 1. And we'd say, yes it is, because over here, just to be very silly about this side here is 1 squared, which is 1, minus 0, so I get a 1 here. And over this side, it's 2 minus 1, which is 1. So we say, definitely true for this. Now then, let's look at the next one. Now, rather than just writing 2 minus 1, why don't we just write it where we've it worked out first, and we'll say 1 squared. And over here, we're saying it's going to be 2 by 2 minus 1. Down here, we're saying 3 squared minus 2 squared is equal to 2 by 3 minus 1. And you can see how it runs. Now, we've been asked to look at a particular interesting thing here, which is the sum of these things. What if I was to sum up these, even the few we have at the moment? What you will notice is I have a 1 here, or a 1 squared, and I'm taking away a 1 squared here, okay? I've got a 2 squared here, and I'm taking away a 2 squared here. So rather than adding up a big long list of numbers down along here, and take away a second long list of numbers down along here, what we do is we say, I can get these two to kill each other, those two, and it'll happen the same way down along here. And the funny thing is, up at the very top, we're only left with this minus number up here. What happens down at the low end? Down at the low end, you get to a situation where we'll write in the lowest one first. It's n squared minus n minus 1 squared equal to, if we go to the one ahead of it, we will say it's n minus 1 squared minus n minus 2 squared, and we'll go, aha, these cancel each other also. The implication is these will cancel. Now what you will notice is these somewhat diagonal lines I've drawn, they're all the same slope. So the front one in a line is neutralized by the second one in the line below it, and that goes all the way down. And now what are we left with? Down here we're just left with this number here, which is n squared, and the number up at the top right hand side here, which is minus, and I'll write it as I had it, okay? And 1 minus 1 squared, as we know, is 0. Yeah? And over this side, what have we got over this side? Well, everything seems to be in the first part here is multiplied by 2. And the numbers that have got multiplied by 2 are 1, 2, 3. So forget the multiplied by 2 for the moment, and we're saying I want to add 1, 2, 3, and on and on and on as far as n. Okay? So we can now say that we've got twice all of these numbers. Okay? And we've just got a nice constant being taken away every single time. So we have got, it's minus n. We have n of these ones being taken away. We've been given a result for this sum here. I'll do it the long way for you. But it was multiplied by this 2 here, so they cancel. So what we can say is that implies and you can ask yourself, is that true? And it is true. But the nice thing is, you've been introduced to a very powerful tool, and the tool is this way of, even though we've got a long line, and there could be thousands of these lines down along here, we've got a long line of them, and yet, because they love to neutralize each other out, this huge thing telescopes down into just this minus that. They don't all work exactly the same as that, but in reality they're all that simple. So we can look at a few examples of these. Now this first little bit is to just introduce you to a little trick, because one of the things you'll often have to do is you'll have to break up a term like this into its two simpler terms, like that. But the real question that they want to ask you is find Sn, which is this sum as r goes from 1 all the way up as far as n, all over 1, all over r. They're saying we want to find the sum of these things here. Now obviously if you had 1,000,000 of them, that would be an awful lot of numbers. Well, one of the first tricks is if you can break an expression like this into a simple expression minus another simple expression, the likelihood is that you can telescope the series down into something very simple. Okay? So what's the little trick? As a general way of dealing with it, now it's quite easy here because you've 1 up the top, but the basic trick is you can say, I'll draw a line over here, and now you deal with this as you would have always dealt with it. You find your common denominator and you cross multiply, so you get a outside of r plus 1 minus b outside of r, and you'll say, how many r's do I have here? And what's my free number? And what's underneath the line doesn't really matter now, because what we can look at is we say up here there's only a constant, okay? there's no number multiplying into an r up there. Well, if that's the case, that guy must be 0. Okay? And we would say to ourselves, I have a free number, this 1, so I'd expect my a to be that. Now, that'll work for any of these things. It's the easy way to break it up, and all that happens is you finish up with 2 simultaneous equations and you play with them. They have given us the opportunity to go and prove it. Now, one way of doing it is when they've told us the number that's up here and they've told us this number already, you just go and you work it out. And having worked it out to say, yes, it's true. But if they didn't tell you what the number up here was, or the number up here, you have to use an A and a B. So let's look at telescoping this thing. Even by the time you've got to 2 of these, what you will notice is that they are now cancelling each other. If we did write in the third one, what we would have would be obviously 1/3 minus 1/4, and you can see they cancel, and they'll all continue cancelling. Now, just one little note that you will require just to keep in mind is that you can see there's only one little term left up here. Down at the very bottom of this series, down close by the n, the un one, you will only get one down here that is left without being killed out by a minus version of it or a plus version of it. So let's get, what that then means is I only need to write the last one. This one will be cancelling with the one just above it, and everything up along, they will all cancel away, and now all I'm left with is this guy minus that guy. So when I sum it up, I will get 1 minus 1 over n plus 1. Now, I think it's much easier to work out the sum of a series when we know an equation like this. It's way easier than having to work out a huge number of lines like this. Telescoping is a really powerful tool. It's not difficult. All you have to be is systematic about it. I will deliberately just go through another one of these simply so that it'll show you can finish up with 2 at the front and 2 at the underneath. Generally you won't finish up with 3 or more for the Leaving Cert. So let's just look at this. And it'll also show you the A and B thing. Now, while we only have one term like this, you can't telescope, because remember in the telescoping it's a term minus another term. So what we'll do is we'll set about breaking it up. Now, again, how many n bits do you have? And how much free numbers do you have? Oh, we don't need to worry what's underneath the line, because what's underneath the line here is the same as what's underneath the line here. But what we can say is there's nothing up here that is an n term. There's no like 3n or 7n or anything. That means what we can now say is that a plus b, this guy, must be equal to nothing. What we can also say is there's a number 2 up here, and that must be equal to the free term here. So and from that we can work out the b. So then we can say that this thing here is equal to okay. Now let's look at the telescoping of this. What's it equal to? The first one, 1 all over 1. Which we know, obviously, is 3. And now I'll just write it as 3 for you. Okay, the second one is 1 over 2. Notice that 1 over 2 is not going to get cancelled by the 1 over 3. Okay? And now I have 1 over 4. The third one, that's the interesting one, because we had to get all the way down here before we got 1 to cancel. So the slope of this line is steeper than in the previous ones because it's missing out a whole 2 terms up here. Once we've established this sloping cancelling line, everything else will cancel the same way all the way down. But we have a term left here from the first one and a term left from the second one. So now we know when we get down to the very underneath of this series that we'll need at least the last 2 lines in order to be able to complete the work on this. So let's look when r is equal to n, which is the un one. We get it equal to 1 all over n, and we look at the one above it. I always find it easiest to go to the very bottom one rather than trying to work out the n minus 1 one, because it kind of does your head in a little bit trying to work it out, whereas if you have this line already established underneath here, you can work it out much more readily. Any place that you have an n down along here, you'll be replacing in the line above it with an n minus 1. Now, n minus 1 plus 2 is what we need to consider here. Now, what do we know? We know that our cancelling is going to follow a very particular pattern. We're going to find that this one here will cancel that one, and the one that was above it here will cancel that, and they'll all follow the same pattern, and we're going to be left with two numbers back here because we got left with two numbers up here. So we will say the sum Sn is going to be equal to the 1 plus a half, going to be minus the 1 all over n plus 1, and it's also minus the 1 all over n plus 2. So that's easy. Now, there are quite a number of examples given in the books. They're worth doing because it doesn't take a lot of practice, 3 or 4 of these, and you'll really get it in your head. And it has this really great habit of coming up quite a lot in the exams, I mean. So then, that's the first half of the series and sequences chapter. When I say half, I mean half by way of the lead-in, the get used to the concepts, and the introduction to telescoping series. The second half is where you start to look at sums of very particular types of series, which are the arithmetic series, the geometric, and a small look at arithmetical geometric series. And that will also bring in limits. Something that you have to know for your calculus and also for the special question. But that'll be in the next talk. Okay? Bye now.